Now here's what I want you to take down in your notebook. If you had like your own gold sheet, or if you had an open space on a gold sheet, or just put it on your own note sheet, whatever, these are your notes, do it however you want. Take this down. And what we're gonna do is we're gonna translate these words into the formula and do an example for every one of these, okay? So, if you listen carefully to what I say, doing this stuff in the future will make more sense, like when you're doing the homework, okay? Having this with you when you're taking the assessment is gonna help you a metric butt ton, because there's a bunch of weird rules, and the rules for logs are just wacky and different. I'm gonna find a Quizlet or something online that'll help you practice outside of the in-class practice stuff. I will make it an assignment, make sure you do it, but just so you know, that's all gonna be out there. Logs are the kind of thing you just need to try and do and do and do and do until you just go, I got this, So, first thing with logs is that the log of a product is a fancy word for multiplication. So the log of two things being multiplied is the sum of the log of the factors. Translated, the log of two things being multiplied is the sum of the log of each of those things. So multiplication turns into addition. That's what happens. Multiplication becomes addition. That's what they're saying. It's just a trick with logs. And by the way, if you're given this, and if you're told to make it into a single log statement, you can translate going back the other way. You can take this log, this addition log thing, and go left and make it multiplication. That's totally okay. So, what they mean is, what if I had this example? Well, it's log of 1,000. If you remember from our last lesson, a regular log is log base 10. I know, for example, that 1,000 is 10 times 10 times 10. So I could actually write 3 log statements because I got 3 separate things that are being multiplied. So I can write that as log base 10 of 10 plus log base 10 of 10 plus log base 10 of 10. And what's funny, and I don't mean ha funny, but what I did was I broke it down in the way I did for a reason. First of all, remember when we're trying to figure out what number this is and we don't have Desmos or a graphing calculator or whatever, what you can do is you can just think, well, wait a minute. This is supposed to be, like if I look at just the log base 10 of 10, and I need to figure out what that equals something, and we can do that swirl thing where we can work our way around and do this sort of little swoosh thing. So this means 10 to some power is equal to 10. 10 to some power is equal to 10? Well, that's just 1. 10 to the 1 equals 10. So that means this is just 1. And so is this. And so is this. So strangely, the answer to this thing is 3. And by the way, I could have skipped all of this and just started with this. 10 to the something is 1,000. 10 to the something is 1,000. And if I remember my exponent rules with tens, 10 to the third is 1,000. Right? I could have skipped all this, but I just wanted to point out to you that the fact that I broke it up is as legit as if I didn't break it up. It's all good. Next. If a quotient, fancy word for division, if a quotient or a fraction, you got a log of something dividing something else, the log of a quotient is the difference of the logs within. It's always top minus bottom. So if you look, log base b, doesn't matter what the base is. What matters is what's happening in here. Like, same with that. Log base b of a divided by c is log base b of a minus log base b of c. You're just subtracting. Division turns into subtraction. And like I said earlier, if you're given a big, long, crazy expression and they say, hey, could you simplify that? Could you simplify that into a single log expression? Yes, I can. Yes, I can. You just need to remember that subtraction turns into division, and it's all kosher. So let me get back to this, log base 2. By the way, your graphing calculator, handheld calculator, Desmos, doesn't have a log base 2 button. So I'm going to come back to that. But I'm not worried about this because this is going to come out nice, clean, and neat. Log base 2 of 16 over 2 is the log base 2 of 16 minus log base 2 of 2. Now if you've picked up on this, but I'm going to save us some time here. When the base and the thing that's sitting next to this match, the answer is always going to be 1. 2 to the 1 is equal to 2. 2 to the 1 is equal to 2. So I know that this number is just good old-fashioned 1. 2 to the something something is 16. Like 2 to the what is 16? Well, I can just use my little thinners and figure it out. So 2 times 2 is 4, times 2 is 8, times 2 is 16. It's 4. So that means this is just 4 minus 1. Oddly enough, this number is 3 as well. Also, by the way, we know 16 divided by 2 is 8. Log base 2 of 8, what is that? 2 to the something, 2 to the something is 8. 2 times 2 is 4, times 2 is 8. That answer is 3. So I could have just simplified this and found the answer that way, but I just wanted to use our new rule to show you that it's legit. Next, getting back to the English, the log of a power. So I got the log of something, but it has an exponent on it. This, by the way, right here is the whole reason they developed logarithms. There would be an x sitting there, and I would have a number to a power of x. Or God forbid, I would have an x thing to the power of some x thing. Like x squared to the square root of x. These nerds developed this thing called logarithms just to deal with the x in the exponent. And we'll get to that in a second here. So the log of a power is that power multiplied by the log. Notice what happened here. The a no longer has the c on it. The c is now in front. It's the power times that logarithm. So what happens is that the power drops down and it becomes what's called a coefficient. It becomes a number out front. So if I do that here, I really have the 3 coming down, and I get 3 times log of 10. Well, that, I know that's base 10. Remember, when there's no number there, the base is 10. And oh my gosh, here we go again, log base 10 of 10, log base 10 of 10, log base 10 of 10, all of those were 1. That is just a 1 times 3 is just 3. You're thinking these other answers are going to be 3 because the first 3 were 3. You're probably thinking that. I'm sure you're thinking that. Let's see. So you've got the product becomes a sum, the quotient becomes a difference, and the power becomes a coefficient. The power comes down in front. Okay, here we go. 2 more rules. Logs of exponentials of the same bases are inverses and they cancel out. So in other words, check out that base. The base of the log and the base of the thing that is inside the parentheses. Those match. Same thing here. The base is a and the base of the log is a. They match. And so what you could do is you could think of it as, it's kind of like taking the square root of something and squaring it. Or something is being squared and you're like, yeah, I want to take the square root of it. The square root and the squaring cancel. It doesn't matter which one you do first. They are opposite functions. They're inverse operations. They undo one another. You pull your sock on, you pull your sock off. They undo one another. They're opposites. So these, you could think of it as like all this junk burp cancels and you just get that A. Same thing here, all this junk burp cancels and you just get the C. So when I look at this, oh wait a minute, what's the base? Oh, that's right, when there's no number, the base is 10. Oh, that base matches that base, my answer is 7. 10 log, oh yeah, even up here, and I know this looks weird, but in these examples, I can have a log up in the exponent. When you take more and more math, you're going to find that any drunken fool can put whatever they want in the exponent, including log base 10 of a number. And the base and the base match, they cancel out. This is 7. The answer was going to be 3. Silly. Okay. Logs with unusual bases, not 10, not the number e, and we're going to get to the number e pretty soon, can translate to regular bases like 10 or e. The whole thing, this is called the change of base rule. The whole thing about the change of base is because we don't have calculators that can do log base 2. We just don't. So what we do is we trick the calculator into doing log base 2 or some other base. Like, for example, if I have a problem that says something like log base 17 of 6, and they want me to know what that is, I need some way to translate that into a log that my calculator or Desmos can handle. So, okay, here I go. This is log base b of a translates into the log of a over the log of b. Notice that in this case, it's really log base 10. Now, this last piece that I'm writing, you don't need to write, and you don't need to worry about with the calculator or with Desmos, because when you just say log, it just means base 10. But I'm putting it here because you notice the bases match. Okay? So I want to point out something about this little formula, and it's important that you highlight this in yours. You see how the base kind of sits lower than the thing you're taking the log of? See how that's on the bottom? And you see how the other number kind of sits above the base? And you kind of see how that sits on top? That's how I know what goes where. So like log base 17 of 6 is the log of 6 over the log of 17. And by the by, I want to take this opportunity to simply go to Desmos and show you how you would use Desmos to calculate that. So, it's a pretty sweet little online calculator. Again, please put it on your smartphone. It's nice. So, let's see here. No, I don't want to do that. Here's what I'll do. I'll cancel that out, and I'm just going to type in what that said. That said log of 6, and now I'm after the parentheses, divided by log of 17. And it gave me the answer, 0.632. Just like that, it's just sitting in there. So you can just, instead of worrying about what the graph would be, you could just type in something that you have to figure out, right in Desmos, and you are golden. So now I can write that down in my little example here, 0.632. Now, I'm good with this, and I'm good with this. That's the exact answer. If you notice, there's a lot of decimals there, and I just rounded to the first 3 decimals. But I just want to point out to you that that's an approximation, the decimal, that's the exact answer. Okay, so that's the notes I want you to take down. Next video, we'll go through the examples from the book.